Why corn? Corn is the world's premier energy crop. Indigenous Americans engineered a nondescript grass into the world's premier solar energy collector. Each acre of corn produces twice the biomass as an acre of temperate forest or grassland. 40% of the energy captured from the sun is concentrated in the ear of corn. Each kernel of corn is a golden nugget of energy encapsulated in a hard shell. This results in a dense energy source that is easily moved and stored. Conventional methods. Corn is an annual plant that grows best midsummer when sunlight is most intense, and the temperature is 80 to 85 degrees Fahrenheit. The historical way of growing it is to turn all the soil over and to break it down into small pieces with harrows. Conventional compaction. Plowing and harrowing create layers of packed soil that prevent the water or roots to pass. This compaction is a major problem in high clay soils like we have in the Champlain Valley. Crop yields are reduced when it is present. Breaking the compaction. The shank point and wings lift the soil. This action fractures the compacted layers without disturbing the surface residue. Fractioning the compacted layers allows rainwater to infiltrate the soil rather than running off. Plant roots go deeper. Plant roots are able to follow the fracture and access the water that infiltrated the soil, rather than being restricted to only the top layer of soil. Strip tilling. Strip till breaks up the compacted layers by going below them and lifting the soil without turning it over. This also conserves the protective surface, organic matter, and reduces erosion. Shanks break up compaction. Strip tillage only disturbs a 10-inch wide strip every 30 inches. The shanks go below the compacted layer and lifts the soil. Fluted coulters then break up the lumps. Lastly, a rolling basket levels and firms the soil prior to planting. GPS guidance is needed to maintain every pass exactly over the prior passes. This ensures that the seed and fertilizer is always placed within the tilled band. GPS guidance was used to steer the tractor. It is needed to keep each pass over the field identical to the previous passes. This beacon provides a GPS correction signal. This signal is required for accurate positioning of every pass in the field. Pass-to-pass reproducibility is essential for accurate seed placement within the tilled strip. First, the winter cover is killed with generic glyphosate. A week after spraying, it is okay to work the ground, even though the plants are not yet dead. This is a view of the strip being made. This is a view of the strip tiller operating. This is the planting tractor of the strip builder in operation. This is the soil after strip tilling and planting the field. Only the soil where the corn will eventually be planted is disturbed with strip tillage. As you can see, only a narrow strip has been disturbed. Here the cover crop is not yet dead 1 week after spraying. Here, the planter is following the strip builder. In 2010, it was too wet to build the strips in advance. For this reason, we planted immediately after the strip builder, between rain showers. This is a sod field immediately after planting. Please note that all of the organic matter remains on the surface as mulch. Closing the seed slot was a problem this year. The clay was very wet due to excessive rainfall during the previous 3 weeks. To close the seed slot, we dragged a pulvy mulcher over the field with the teeth barely touching the surface. This scuffed dirt over the seed and closed the seed slot. Emergence was comparable. The strip-tilled corn above emerged at the same rate as the conventional corn below. The light green is a mixture of emerging weeds and dying weeds in the strip-till plots. 2 weeks later, we reapplied glyphosate to both plots. Strip-till rows of corn. The corn in the foreground suffered from wet feet. The water migrated along the slots to the lower spots, stunting this corn. Later, after it dried out, this corn had water when the other did not, and caught up. This is the same corn 2 weeks after the previous picture. Please note that where the corn looked better 2 weeks earlier, the loss of nitrogen has set it back. Residue. After harvest, 60% of the organic matter is returned to the soil. This provides mulch and soil cover for the winter. The added organic matter sequesters carbon in the soil. The time needed to plant was half of what was needed for the other conventional methods. There was approximately a 25% reduction in fuel cost per acre with strip tillage over the conventional methods. Comparison. At full maturity, there is little difference between the strip-tilled corn on the left and the conventionally tilled corn on the right. The corn on the left was strip-tilled while the corn on the right was chisel-plowed and harrowed. The field is a flat, wet field. The strip-tilled corn was deeper rooted and suffered water damage. The chiseled was better but tended to fall over in the fall. The corn on the left was strip-tilled before planting. The corn on the right was moldboard plowed in the fall and in the spring harrowed. There was little difference in appearance between them. For more information, visit us at www.vermontbiofuels.net.